in 2016 as well, in the long questions, there was another differentiation calculation. Now, the first bit of this is through related rates of change. Now, when you're doing related rates of change, I always work with the fact that whatever we're trying to find, we work with what we're given and what we need. Now, a lot of the formulas here are going to be based on your area and volume formulas there on page 10 and 11. So keep that page open when you're doing these calculations. So air is pumped into a spherical exercise ball. Just the important thing there, it's a sphere. At a rate of 250 centimeters cubed per second. So when you see centimeters cubed, we know that's volume per second over time. Find the rate, that's what you're looking for. Find the rate at which the radius is increasing. So once you see rate, that's over time. Rate is definitely something over time. And in this case, the rate is going to be the radius over time. The radius is increasing when the radius of the ball is 20 centimeters. So we'll just slap in 20 centimeters in for R in our final answer. Give your answer in terms of pi. Leave pi in your answer. So what are we trying to find? Find the rate at which the radius is increasing. So we're trying to find dr dt. What are we given? We're given that it's a sphere. So two things we know about a sphere is that its area or surface area is 4 pi r squared and its volume is 4/3 pi r cubed. Now they've given me the volume bit. So the volume is 4/3 pi r cubed. So the rate of change of the volume with respect to time, so dv dr, the rate of change of volume with respect to the radius, multiply down to the power. 3 times 4/3 is 4. Put it in your calculator if you're unsure, and reduce the power by 1. So dv dr is 4 pi r squared. So that's what we're given. And what do we need? So in order to work out what we need an r in the top and a t in the bottom. So definitely something over dt. And we need a dv. Sorry, we go dt times drdv dt, and we just change the order of this. So about that, let's see. So drdt is dv dt times drdv. Let's see, they both go with each other, and we're left with drdt. Yeah. So the rate of change of volume with respect to time is a 250 centimeters cubed per second. Volume centimeters cubed, time in seconds. So drdt is 250. They've given us that, times the rate of change of radius with respect to the volume is just the inverse of this. So dv dr is 4 pi r squared. Therefore, if we flip this over, drdv, we flip this over, and that's, remember, over 1, so it's going to be 1 over 4 pi r squared, and that's tough. Just when we're multiplying fractions, top by top, bottom by bottom. So 250 over 4 pi r squared is our drdt. And here they give us a certain value of our radius, which is 20. So 250 over 4 pi times 20 squared is drdt. We'll just plug that into your calculator in terms of pi, so we'll leave pi in our answer. Over 32 pi. So in that case, I just put in the numbers, changed from 7 back to degrees, and left the pi in it, the rdt. So it wasn't giving me my answer in terms of pi. And that is the rate of change of radius with respect to time, so 5 over 32. If you like your units, radius is measured in centimeters, time seconds. The second part. Find the rate. So again, find is equal to the given times what you need. So find the rate at which the surface area of the ball is increasing. So surface area, we're trying to find the rate, so over dt. Now if you look in your formula book again, you'll see your area is 4 pi r squared. So we can work out dAdr, the rate of change of area with respect to radius, by multiplying down by the power, reducing the power by 1. So our area is equal to 4 pi r squared. So dAdr is 8 pi r. So we are given dAdr. So that means we've got dA in the top, we want dt in the bottom, we need another dr, so we can cross out and cross multiplying. Now luckily enough, in our previous answer we worked out dr dt. Dr dt, if they didn't give us the radius, we work with this, but in this case, since the radius is the same, since they're both 20 centimeters, we can use this here. So dA dt is equal to dA dr, pi r, times the dt. I'm just going to use this 5 over 32 pi, and squeeze that together, top by top, bottom by bottom. Your pi's will cancel, so 40r over 32, and then we're going to sub in our radius of 20. Just 25. And surface area on the rate, so centimeters squared per second. Now you get no marks for your units, just in case you're unsure. So 25 centimeters cubed per second. The next bit to that, the inflated ball is kicked into the air from point O on the ground, taking O as the origin, which is 0, 0. This here describes the path of the ball, where both x and fx are measured in meters. Find the values of x for when the ball is on the ground. So when the ball is on the ground, the height is equal to 0. So this here just simply minus x squared plus 10x is equal to 0. It's your quadratic. You take out your x, and you're left with minus x plus 10. Let each factor equal to 0. X equal to 0. So there's your two answers. Now the second bit actually is integration. So you can look at this when you're doing integration. If you've only done calculus, don't worry so much about it. Here we know it's going to be integration. It just says here average. So find the average height of the ball during the interval. And they're giving us the interval from 0 to 10 when it's kicked or hits the ground again. So once we see average, you know, using your formula 1 over b minus a, the integral of a to b, f of x dx. So 1 over your b is just your bigger limit, 10 minus 0. Now you've got to integrate that. Increase the power by 1, divide by the new power. Increase the power by 1, divide by the new power. I'm just going to tidy that up. Between 10 and 0. All you've got to do now is lob in your 10, take away your 0. Once you sub it in as well. You put that in 1 over 10 times minus 10 cubed minus 1000 over 3 plus 10 squared is 100 plus 500. Put that all into your calculator. You have 50 over 3 meters.